Okay.
So should I start maybe?
Okay.
Okay, so I will use slides for this lecture 5, and then I will switch to the whiteboard for the next lecture. So the goal of today's lecture is to first, during the lecture 5, I'm going to describe the notion of finite energy classes, explain how to define the Monge-Ampère operator and its range on such energy classes. And then in the next lecture, I will explain a variational approach in order to solve degenerate complex Monge-Ampère equations. So more precisely, I will follow in this lecture 5 a paper that I wrote a few years ago with Ahmed Zeriai on finite energy classes. And then in the next lecture, I will describe the heart of a paper I wrote a few years ago with Robert Berman, Sébastien Buxom, and Ahmed Zeriai. Okay, so let's start. So here again, X omega will denote a compact Guedj manifold of complex dimension n. And so either H omega or K omega, depending on the slides, will denote the sets of those smooth functions on X whose curvature with respect to omega is positive. So omega plus Ddc phi is yet another Kähler form cohomologous to omega. This is the so-called set of Kähler potentials. I will denote by V the total volume of X with respect to this fixed reference form omega. And let me make the following definition. So for a Kähler potential phi, I denote by E of phi, so it is a functional on the set of Kähler potential, and this is the following quantity. It's a summation, so you have n plus 1 term of the integral of phi omega phi to the j wedge omega to the n minus j. And you normalize this summation by dividing by v times n plus 1, so the number of terms. So this functional plays a very important role in the sequel, and it's already illustrated by the following lemma, which says that E is a primitive of the Monge-Ampère operator. So the precise statement is like this. If you take a path phi t of Kähler potentials, then if you differentiate E along that path, what you obtain is the integral of phi t dot against the Monge-Ampère of phi t. And really the way you should think of it is that E prime, the differential of E, is equal to the Monge-Ampère operator MA, so the normalized Monge-Ampère operator. So let me give the proof of this lemma because it is so important. So you see E is a summation of terms. So when I differentiate, I need to differentiate each of these terms. So let me differentiate one of them. If I differentiate this j's term along a path phi t, so I need to either differentiate phi t or differentiate omega phi t to the j. So I get two terms. First, integral of phi t dot wedge omega phi t j omega n minus j. And then if I differentiate omega phi t to the j, what I will get is j times the integral of phi t ddc phi t dot omega phi t to the j minus 1 omega to the n minus j. Fair enough. Now I will integrate by parts on this second term. So you see that integral of phi t ddc phi t dot, I think of it as integral of phi t dot ddc phi t. So this is what I get by doing so, just using Stokes' theorem. And then ddc phi t, which is in the second term on the right-hand side, I think of it as omega phi t minus omega. So I add and I subtract omega. So if I do that, what I get is j plus 1 times the first term minus j times integral of phi t dot omega phi t to the j minus 1 omega n minus j plus 1, because I have an extra omega coming here. So you see, it looks like a telescopic series. So when I make the summation of these terms, so or if you prefer, when I differentiate the total E functional, so modulo this normalizing factor n+1 times V, what I do get is this summation, which is hence equal to a difference of sums. And then I can reindex the first sum or the second one, depending on your preference, and you get cancellations. So at the end of the day, only one term is remaining, namely n+1 times integral of phi t dot omega phi t to the n. So if you divide by n+1 and v, you end up with the formula from the lemma, namely that the differential of E of phi t is integral of phi t dot times Monge-Ampère of phi t. Okay, it's a rather simple lemma, but it has a huge number of consequences. So here is the first one. Because the differential of E is a non-negative measure, so E prime is the Monge-Ampère measure of some Kähler potential, it is non-negative. In particular, it says that the map, the functional phi goes to E of phi t is increasing. And this allows me to make the following, before that, let me, for later on, make a second computation. So I can differentiate a second time. So what do I get in doing so? Well, d by dt of E of phi t was integral of phi t dot Monge-Ampère of phi t. When I differentiate twice, either I differentiate again phi t dot, and this is the first term that you get here, or I differentiate Monge-Ampère of phi t. And then what I do get is n times integral of, there is a typo here, sorry about that. So it should be n divided by v, integral of phi t dot, ddc phi t dot, and then omega phi t to the n minus 1. So you should divide by v the last term on the right-hand side. And then I can again integrate by parts on the last term on the right-hand side. And when I do get is this, and again, the same typo here. So it should be n divided by v times the integral of d phi t dot, dc phi t dot, omega phi t to the n minus 1. And this last term, you can interpret it, modulo this normalizing constant, as the square of the gradient of phi t dot with respect to the Kähler form omega phi t. So in particular, if the path t goes to phi t is affine in t, so if you move along a Euclidean segment in the set of Kähler potential, then the first term is 0 because phi t double dot is 0, and the last term is negative because it's minus the square of the norm of the L2 norm of the gradient of phi t dot. So you see that it's an important piece of information for the sequel. E, the functional E, is first increasing in phi, and then it is concave along Euclidean segment. And we shall see, so not today, but Thursday, that it is interesting to consider another type of geometry, not the Euclidean geometry, but another geometry which is called Mabuchi geometry, along which E will be rather affine rather than concave. And this will have interesting consequences. But this will be a topic for Thursday. Okay, so coming back to the increasing property, which is somehow a bit simpler. So this is what I just said. Let me make the following definition. So I extend the functional E to the whole set of omega prosymmetric function by monotonicity. So I denote by E1 of x omega. This is the set of those omega prosymmetric functions so that E of phi is finite, where by definition, E of phi is the infimum of the energies of the Kähler potential psi, which lie above phi. So remember that we have seen that in the second lecture, in lecture 2 1 week ago. Any omega prosymmetric function is the decreasing limit of smooth Kähler potentials. So you can always you can pick any such sequence, and you look at what you get by taking the decreasing limit of the corresponding energies. And this definition says, well, there are two possibilities. Either sometime it goes to minus infinity, well, or it never goes to minus infinity, and in that case, the corresponding function belongs to the so-called class E1 of x omega. So that's the definition. So which are the functions that do lie in this class? So first, the first simple examples are bounded omega plus omega functions. Namely, if you look at the very definition, if phi is bounded, you can bound from below phi by the infimum, or you can bound it from above by the supremum, if you prefer. And then what remains is a summation of, you integrate then against a probability measure. So the E functional is always bounded from below by the infimum and bounded from above by the supremum of phi. So in particular, if phi is bounded, then you have a uniform control on the energy. But the class E1 contains as well many, and actually very many, unbounded functions. And here is a recipe to construct such. If you start from some omega plus omega function, which is, say, normalized so that it is less or equal than -1, if you make, I told you 1 week ago that if you compose some omega plus omega function by a convex increasing weight, which is conveniently normalized, then the corresponding guy is again omega plus omega function. And here the weight minus t to the power epsilon is an example of a convex increasing weight. So this is no surprise that minus phi epsilon is omega prosomonic. But what I claim here is that if epsilon is small enough, then what you get is a function in E1. And how small should epsilon be? Well, the precise answer is that it should be strictly less than 1 divided by the dimension plus 1. In particular, so I'm not going to give the details here. It's computational. It's not difficult. It's not very difficult, but I won't do that. In particular, you see that somehow E1, in a certain sense, contains as many functions as you already have in PSH x omega. But in order to enter E1, somehow we need to smash a bit the singularities of phi. So imagine that phi, the worst singularities you can imagine are logarithmic ones. Imagine that phi looks like log of modulus of Z1. Then you are raising this guy to a very small power. And this has, as a consequence, has the fact that the new function has very small singularities, is unbounded, but with much smaller singularities. Here is another rather simple property. So if you have two omega corresponding functions phi and psi, and if one of them is in E1, then the maximum of the two is in E1. So E1 is stable on the maximum, and this is a simple consequence of the definition I gave above. And maybe the first good intuition you should get of E1 comes from complex dimension 1. So if X is a compact Riemann surface, then E1 of X is the set of omega subharmonic functions whose gradient is in L2. So the W12 denotes the standard Sobolev space. And why is that so? Well, namely here, the E functional has two terms. So it's 1 divided by n plus 1v, so 2v times these two integrals. The integral of phi omega, well, this one is always finite, because we explained last week that omega plus omega function are in L1. And if you decompose omega phi as omega plus ddc phi, and if you integrate by part, what you do get is this quantity. So E of phi in dimension 1 is the mean value of phi against omega minus 1 divided by 2v times the integral of d phi dc phi. And once again, this quantity here is the square of the gradient of phi. So E is finite if and only if the gradient is in L2. And this explains you why in dimension 1, E1 is simply the intersection of the cone of omega subharmonic function with the Sobolev space W12. It turns out that in higher dimension, you can think of this E1 class as a nonlinear version of this Sobolev space intersected with the cone of omega subharmonic function, omega subharmonic functions. And in particular, it is indeed always true that functions in E1 have gradients in L2. And the proof is a bit similar, namely, you integrate by parts. So let me start with the simplest term, maybe, integral of phi omega n minus 1, which is one piece of the E functional. If you integrate by part, as I did earlier for the dimension 1 case, then what you get is this term. If you do a similar integration by part for the term integral of phi omega phi to the j plus 1 wedge omega n minus j minus 1, this is what you get. And you see that you've got the j plus 1 term is equal to the j term minus the square, minus a positive quantity, which looks like the square of the gradient of phi with respect to mixed term, the mixed measure. And in particular, the j plus 1 term is bounded from above by the j term. So if you put all these inequalities together, what you end up with is the fact that the E functional is bounded from above by the mean value of phi with respect to omega n minus a certain multiple of the square of the gradient of phi with respect to the Kähler form omega. And if phi has been, yes, there is a small kind of typo here. If phi, if you normalize phi so that its supremum is 0, what you get is that the gradient is bounded from above in absolute value by the absolute value of the energy. So if the energy is finite, then the gradient is in L2. Okay. So let me now define the Monge-Ampère operator when acting on these guys. So last Thursday, I explained how to define the Monge-Ampère of bounded omega subharmonic functions. This is the so-called Bedford-Taylor theory. And here we can extend the Bedford-Taylor theory to this slightly more singular setting. Namely, you pick one such function, phi, and you simply cut out the function by taking the maximum with minus large negative constants. So look at phi j, we call them canonical approximants. These are max of phi with minus j. Then the Monge-Ampère measure, Monge-Ampère of phi j, these are well defined by Bedford-Taylor theory, and the claim is that they converge towards a unique measure that we call the Monge-Ampère of the function phi. And the reason why this is true is not very complicated and resembles what I explained last Thursday. So imagine you pick j and k, two indices, with j greater or equal than k. Then observe that the Monge-Ampère of phi j is exactly equal to the Monge-Ampère of phi k in the set where phi is strictly bigger than minus k. And on the other hand, so as a consequence of that, when you look at at these two measures acting in the Radon sense on the test function chi, then what you end up with is that this integral, or the absolute value of the integral of the difference, is bounded from above by by a certain constant, say, times the n infinity norm of the test function divided by k, so k is the smallest of the two indices, times the energy of phi. And the reason is that, so this difference is 0 where phi is bigger than minus k, and where phi is less or equal than minus k, you can actually get rid, use the inequality, you simply bound from above the difference by the summation of the terms, and then you add artificially phi j on the Monge-Ampere of phi j and phi k on the Monge-Ampere of phi k. These two terms will be controlled by the energy of phi on one hand, and the other hand, when you introduce them, you can divide by k, which is the minimum of k in j. So you have this simple inequality that tells you that the sequence Monge-Ampere of phi j is a Cauchy sequence in the space of probability measure. Okay, so let me emphasize that actually the convergence of Monge-Ampere of phi j towards this unique measure holds actually in a rather strong sense. So it holds in the Borel sense of measure, rather in the Bedford-Taylor theory that I briefly discussed last Thursday. The convergence holds rather in the sense of Radon measures. Okay. So in particular, the fact that it holds in the sense of Borel has the following simple consequence. Namely, the Monge-Ampere measures of the function phi j do vanish on peripolar sets. So this is something I was planning to discuss last Thursday, but I was lacking time. So a peripolar set is a set which is locally given by or locally included in the -infinity locus of a prosomonic function. And it is a simple consequence of Chern-Levin-Nyrenberg inequalities that the Monge-Ampere of bounded functions vanish on peripolar sets. So here, since you have convergence in the sense of Borel measures, the Monge-Ampere of phi of a Borel set B is the limit in J of the Monge-Ampere of phi j of the Borel set B. So in particular, if B is peripolar, and since Monge-Ampere of phi j of peripolar is 0, then Monge-Ampere of phi of peripolar has to be 0 as well. Well, important comparison and maximum principles that I did not have much time to describe last Thursday, which are valid in the Bedford-Taylor theory, do extend immediately thanks to this property to the E1 setting. And finally, let me stress that in the definition of E, so E is a summation of n+1 term, but there is one term that is the leading guy, and the leading guy is the integral of phi Monge-Ampere of phi. You can see that from this inequality, which is actually a consequence of the same type of integration by parts I've done in order to prove that functions in E1 have gradient in L2. So if you use these inequalities that are already established, then you can realize that E of phi is finite if and only if the integral of phi Monge-Ampere of phi is finite. So in particular, you see from that, since the Monge-Ampere of phi is a well-defined probability measure, that when you are in E1, then the function phi is integrable with respect to its Monge-Ampere measure. So these Monge-Ampere measures have the same continuity properties as we have encountered in the Bedford-Taylor theory. So if phi j is either decreasing to phi or increasing to phi almost everywhere, then the Monge-Ampere of phi j weakly converge to the whole Monge-Ampere of phi. And once again, you can prove this result as a simple consequence of the result that you know in the case of bounded function. Namely, you pass through the canonical approximant, you use the same, and establish and use the same inequality I was mentioning earlier, and you can somehow, you have a property that says roughly that the Monge-Ampere of the canonical approximants somehow uniformly converge towards the Monge-Ampere of phi. So what you can do in the bounded setting somehow trivially extends or uniformly extends to the E1 setting. And something I did not have much time to describe also last Thursday is that once you know how to define the Monge-Ampère of one function, then by playing with the multilinearity of the determinant and by the convexity of these sets of functions, then you can also define the so-called mixed Monge-Ampère measures. So here is a statement. If phi1, phi n are n functions in E1, then you can make sense of the mixed Monge-Ampère measure omega phi 1, wedge omega phi 2, wedge, etc., wedge omega phi n, normalized by dividing by v, and you end up with a well-defined probability measure, which has similar continuity properties as the Monge-Ampère of one single function. Okay. Now I move on to a very important properties of these E1 functions, namely, as I said, many of these functions are unbounded, but they have rather mild singularities. And here is one way, it's not the only one, but it's an important one, to make more precise the fact that they have mild singularities. So for any function in E1, then the low number of this function at any point has to be 0. The proof goes like this. So last Tuesday, I explained the construction of a local green function. So if you pick local coordinate near point A, holomorphic coordinate near point A, so that A corresponds to 0 in this local chart, you can consider log of modulo of the norm of Z, and in Cn, log of the norm of Z plays the role of a green function for the Monge-Ampère operator. And you want to now take this local model and try to cook up a global omega prosemic function. So what you do, you take a cutoff function chi, which is identically 1 near the singularity, and which is 0 rather quickly, so that chi composed with the log is well defined globally on X. So you have this local chart, you use this cutoff function to cook up a global guy, and then you compute the curvature, so the DDC of that. So what happens is that near the singular point, DDC is positive because you are looking actually at 1 times the log of a holomorphic, the modulus or log of the norm. So it is a prosemic function near the singularity. And outside of the singularity, well, you have killed, of course, the plurisomonicity, but you are looking at the DDC of a smooth function. So the DDC is certainly certainly not positive, but it's not very negative. So if you multiply by a small epsilon, what you will end up with is a function which will be omega prosemic. So the negative part is bounded from below by minus omega. So this G or GA, because referring to the point A, plays the role of a green function for the point A. And so I have used that last Tuesday in proving Skoda's theorem. And this function, as I explained last Thursday, has a well-defined Monge-Ampère measure because it is nice except at one point. So it has an isolated singularity. And the Monge-Ampère of this function, as it turns out, because it is a positive or non-negative measure, it is certainly greater or equal than what happens near the point A. And near the point A, it looks like epsilon to the n times the Dirac mass. So you have a kind of a global ersatz for the property of being a green function for the Monge-Ampère operator. And because these Monge-Ampère measures do charge the point A, a point is a very special example of a peripolar set. In particular, with what I said previously, GA cannot belong to E1. So that's an example of a guy which is not in E1. Now imagine that you have a function phi, now an arbitrary one, which has a positive Lelong number at point A. Then by definition, we can find constant C and gamma so that phi is less or equal than gamma GA plus a constant C. So now remember that I explained that E1, it's a simple consequence of the definition, is stable under maximum. So if U is less or equal than V, and with U in E1, then V, and V omega prosumonic, then V should be in E1. But by contraposition, we conclude that phi with a positive Lelong number cannot be in E1, because if phi were in E1, then gamma GA plus C would be in E1, and we have just explained why GA is not in E1. Okay, so this is a rather simple argument in order to make sure that functions in E1 have zero Lelong number everywhere. And with the Skoda's uniform integrability result that I explained last Tuesday, we end up with the following. We will use this property very soon in a few slides in order to establish a very strong Skoda type integrability result. But before that, let me explain something that is quite useful and that I didn't have time to discuss last Tuesday, which is the following. So imagine you have phi j, which is a sequence of omega paraharmonic functions, which converge to phi, say, in L1. Then I make the following construction. So I take the supremum of this function phi L when L is greater or equal than J. And I take the upper semi-continuous regularization. Then my claim is that this guy is omega prosumonic. And moreover, by definition, this is obvious, capital phi j is greater or equal than the phi j I started with. And the final point is that this phi j decreases at all points towards the function phi. So in other words, as I explained on various occasions, it's quite useful to sequences that do better than converge in L1. We are more comfortable for the continuity properties of the Legendre operator if a sequence decreases towards its limit. And here, this proposition gives you a recipe starting with a sequence that only or simply converge in L1. It's a recipe to look up another sequence which is much better behaved. And the proof, let me explain briefly why this proposition holds. It relies on the following facts. So first, let's consider this first item. So I take the supremum of the phi L's when L is greater or equal than J. Then when I do that, if you look at the sub-mean value inequalities that a paraharmonic function should have, then they do satisfy that. So and this is the strongest or the most important property within the paraharmonicity. So somehow the supremum is almost omega paraharmonic, but when taking supremums like this, you are losing in general the upper semi-continuity property. So this supremum satisfies the right mean value inequalities, but we are possibly lacking the upper semi-continuity. But actually, we lose it on the lack of upper semi-continuity is only at a few places, and at least we can say that the equality holds. So between the supremum and the upper semi-continuous version of the supremum, this equality holds at almost every x. And once again, this is a consequence. So this second fact is a consequence of the mean value inequalities. When you write down the mean value inequalities, then the mean value is actually continuous in the point. So what you get is something which decreases almost everywhere towards the supremum. Now, as a consequence, the upper semi-continuous regularization of this supremum is omega paraharmonic, and it is clearly decreasing in J, so it decreases to some function phi. On the other hand, with this property. On the other hand, and this is a property that I did not recall, which is a property that comes from pre-isobornicity, if the function phi j that I start with, the sequence phi j, converges towards phi, then at all points x, the lim sup of phi j at x is less or equal than phi of x, and with equality almost everywhere. So if you put all these informations together, what you end up with is that this decreasing limit capital phi is actually equal to your original limit little phi at almost every point. But now if two periosomnic functions are equal almost everywhere, then they have to be equal everywhere, as I emphasized in the first lecture, or second lecture. Okay, it's probably too fast, but keep in mind this nice recipe. I start with a sequence phi j that converges in L1, and then I cook up this envelope that converges in a decreasing fashion. So let me use this fact on this recipe immediately in order to prove the following important property of the functional E. So I claim that E is upper semi-continuous with respect to the L1 topology. And perhaps simpler is that it is continuous along decreasing sequences, so for a slightly stronger way of conversion. And the proof goes like this. You pick phi j that converges to phi in L1, and you use the recipe I've just described. Then this capital phi j decreases to phi and lies above a little phi j. Therefore, on one hand, I have E of phi, which is the limit of E of the capital phi j. This is the continuity property that I mentioned in the proposition. It's, if you like, a slight improvement of the continuity of the Monge-Ampère operator. It's a continuity of phi Monge-Ampère of phi along decreasing sequences. And on the other hand, E of capital phi j is greater or equal than E of small phi j. Hence, by putting this together, the E of phi is greater or equal than lim sup of E of phi j. And this is precisely this upper semi-continuous property. Okay, and as a consequence of this proposition comes the following remarkable fact. If you look at the sets of those functions in E1, which have the following two properties. So first, the supremum is bounded from above, say by a fixed constant C. Second, the energy is bounded from below by a certain constant minus C. Then such a set is compact for the L1 topology. And the reason is twofold. First, it is closed because the two conditions are closed. The sup condition is closed because of Hartog's lemma that I recalled last week. And the E lower bound is closed by upper semi-continuity that I've just right now. Now, the relative compactness follows from something I already said last week, namely that once you are in E1C, then the supremum is bounded, stays bounded in between minus C and C. Hence, E1C is a subset of a much larger class, which is PSHC of X omega. And this class, I explained last week that it is compact for the L1 topology. So on one hand, E1C is relatively compact by this second information. And on the other hand, it is closed by what I just discussed. So it is a compact subset for the L1 topology. And now I can deduce from that a very nice Coda type result. Namely, if you pick any positive lambda, and if you fix any constant C, and if you look at the integral of exponential of minus lambda phi dvx, where phi moves in this E1C x omega, then I just explained two things. E1C is compact, and secondly, any function in E1C has zero Laurent number. So this is precisely the type of hypothesis I was needing last week in lecture 2 in order to get a uniform Skoda type result. I did not prove exactly this one. I proved another version, but it's very, very much connected. So this set of functions is uniformly exponentially integrable with a constant lambda, which is as large as I want, because we are staying away from positive Lolo number. Okay, so this is, I won't say more today about that, but this was discussed at length in lecture 2. And maybe a final remark here is that, as we will see, we will work with measures mu we have already encountered, which are, say, absolutely continuous with respect to Lebesgue measure, with a density which is in LP for some p bigger than 1. Then here, I have the same theorem, the same exponential integrability theorem, replacing dvx by f dvx simply by using Hölder inequality. Since lambda is as large as I want, I can replace dvx in the statement by f dvx as long as f is in LP for some p bigger than 1. Okay? So you will soon see how this type of measure show up in Kähler geometry. Okay. Now there is a drawback though, that the Monge-Ampère operator is not continuous for the L1 topology. So there is a notion in this context of slightly stronger topology, which is actually somehow the closest topology, which makes this E functional continuous. So this is a second definition. And a practical criterion in order to understand convergence for this topology is that a sequence converges for this topology if and only if. So on one hand, you have a convergence, say, of the supremum, so which is a minimal type of requirement, and then a certain I functional of the difference converges to 0, where I is the following quantity. So you look at integral of phi minus psi, Monge-Ampère of psi minus Monge-Ampère of phi. It turns out that by integration by part, this is non-negative. So I did not give a name to this. When was that? Last Thursday. In lecture 4, we have encountered this quantity. It showed up without a name in order to prove uniqueness of solution to Monge-Ampère equations. When I explained the Calabi argument in order to prove uniqueness of solutions, we actually use this kind of quantity. But never mind. It turns out that square root of I satisfies a quasi-triangle inequality, which means that you have a triangle inequality, but with a constant which is not 1, which is a uniform fixed constant. And in that case, standard topological argument says that this I functional is associated and induces a certain distance. And this distance here is a bit abstract, but next Thursday in lecture 8, I will make this distance more practical and more geometrical by using the Maibuchi point of view. So wait a bit for this better point of view. But it turns out that with this distance induced by square root of I, E1 is a complete metric space. And the space of Kähler potential is dense within E1 for this topology. As one would expect, this was the raison d'être of this topology. The Monge-Ampère operator becomes continuous for this strong topology. And maybe a final word is that this is exactly what you would expect in complex dimension 1. Namely, this I functional is nothing but the square of the gradient of the difference of phi minus psi. So when you take the square root, you get the L2 norm of the gradient. And therefore, the strong topology is exactly the Sobolev topology in complex dimension 1. Okay, so in higher dimension, it's more involved, of course, but it's a sort of non-linear Sobolev type topology on the space E1. Okay, Now, let me move one step further by describing another or a slight extension of the E1 class, which are called EP classes. So let me pick P, real number greater or equal than 1, and look at the subset of E1 of those functions in E1, so that phi is not only in L1 of the Monge-Ampère, but also in LP of its Monge-Ampère measure. Then we have similar properties are for E1, namely at first, any bounded omega prismatic function is obviously in EP for an EP. EP contains a lot of unbounded functions, but you need to be more demanding. So the same recipe cooks up functions in EP, but you need to raise to a small power, which is even smaller than for E1. So you need to raise to a power strictly less than 1 divided by n plus p. So the same recipe works, being a bit more demanding. And in the same spirit, if you are even more smashing the singularities, if you look at minus log of minus phi, then you end up with a function which is in EP for any p. One can, and actually one should consider many other weighted energy classes. So one should leave somehow the world of Lebesgue type condition and entering the world of Orlick's classes. And it has some interest. It allows to interpolate between objects that do not charge peripolar sets to the Bedford-Taylor theory. So I won't do that. I won't discuss that today. It would bring me too far. But let me simply stress that E1, the one that I spend the more time discussing, is the most important for application, especially this will especially become clear in the next lecture. And in a certain sense, more geometric sense, E2, so for P equals 2, is somehow the most natural with respect to the Mabuchi geometry that I will very briefly discuss next Thursday. And maybe these classes will take a special form on a very particular class of manifolds that I'm describing now. Oh no, that I'm describing in one slide. So let me, before describing special examples, discuss the range of the Monge-Ampère operator and simply stating two important results. So first, if you pick one probability measure, you wonder, it's natural to wonder whether it is the Monge-Ampère of a finite energy function. And the answer is kind of beautiful. Mu is the Monge-Ampère of a function in EP, if and only if EP is in LP of the measure mu. So you have a complete characterization of the range of the Monge-Ampère acting on those classes EP. In a slightly different direction, so you will have a brief glimpse of the proof in the next lecture for P equals 1. And in a slightly different direction, and a bit more connected to something I said last Thursday in lecture 4, if you pick a measure, mu, which is absolutely continuous with respect to Lebesgue, and which has finite energy, which means simply here that the integral of f log f dvx is finite. So such measures play an important role in Kähler geometry in various ways. So such a measure is the Monge-Ampère measure of a unique normalized finite energy guy. And it turns out that phi mu here belongs to EP, where P is n divided by n minus 1. And this exponent is sharp. So you see that for n equals 1, something spatial arrives. And it turns out that in complex dimension 1, finite entropy measures have bounded Monge-Ampère potentials. So the statement is correct, but actually one can be more precise. In dimension 1, finite entropy implies finite potential. But in dimension greater or equal than 2, this is no longer the case. So you can be a measure with finite entropy. Then you have a unique finite energy potential, but this finite energy potential is usually not bounded. And this is something important in various ways for applications in Kähler geometry. Okay, so to end this lecture, I'm now going to discuss a special class of Kähler manifolds, the so-called Tauric manifold. So I assume that X omega is an equivariant compactification of the torus C star to the n. Then omega, and I assume that omega is toric as well. So if you like, this is a very good class of examples with lots of symmetries, and one of the only type of examples where we can actually compute more or less explicitly Monge-Ampère measures. So if you restrict omega to C star to the n, then there is a global Ddc lemma, and this omega turns out to be the Ddc, or the IDD bar, of f composed with L, where f is a strictly convex function on Rn, and L is this logarithmic map, log of z1, etc., log of zn. And as a fact, which goes back to the 80s with the work of Delzan, it turns out that the gradient of f maps Rn to a compact convex polytope P, which essentially only depends on the cohomology class of omega. It does not depend on the representant that you picked. And if you pick a Kähler potential, then you look at the corresponding convex function f phi in Rn, you look at its Legendre transformation, then this is some strictly convex function that I denote by g phi on the convex polytope. So here is an example. If you pick x is Pn, omega is Fubinish 2D, this is an example of a Tauric manifold, then the corresponding polytope is the simplex, or you can normalize it to be the simplex, so a set of S in Rn with any coordinate which is non-negative, and the summation of the coordinate is less than 1. And the F convex potential of Fubinish 2D is exactly 1/2 of the logarithm of 1 plus the sum of the e to the 2xi. And if you look at its Legendre transformation, which is by definition this quantity, so g of s is this guy, then what you get is that g is given by this quantity. So g of s is plus infinity outside of the simplex, and it is 1/2 of this sum of si log si plus 1 minus sum sj log 1 minus sum sj. And this is a special case of a beautiful general formula of Gilmin, but which is very so explicit that you can, I leave that as an exercise right here. Okay, so that's for kind of the general frame. What about omega prismatic functions and finite energy guys? So if you pick some toric omega prismatic function, then it corresponds to a function f phi, which is convex on Rn and with certain growth constraints. And f phi is simply given by this formula in C star to the n. F phi composed with L is f composed with L plus phi, where f is the convex potential for omega. Now, if you look at the Legendre transform of g phi, what you end up with is a certain convex function with support on P. What it means, the notion of support here, you should understand that this function, this Legendre transform, will be plus infinity in a huge set, and the place where it is finite is contained in P. So it could be plus infinity in a large part of P, but it is certainly plus infinity outside of P. And here is an understanding of the finite energy classes, namely, if phi, a function phi, is toric and in the finite energy classes EP, if and only if its Legendre transform is in the Lebesgue class LP of the polytope and convex. It has to be convex because it is a Legendre transformation. So I guess, well, I don't have time to describe the proof of this, but at least it gives some kind of naturality in considering those finite energy classes EP. So you see that for in this very symmetric setting, after Legendre transformation, you can read off everything from what happens on the polytope. And here you are dealing on the polytope with Lebesgue spaces. So it's kind of natural spaces to consider. And in a somehow different flavor, as you know, L2 is the most geometric or the most perhaps better behaved of the Lebesgue spaces, and that this one corresponds to E2. Okay, so a very, very, very special case is when X is P1, so you're in complex dimension 1, then you are doing convex geometry on the unit interval 0, 1, and this corresponds to considering radial examples that I described a bit in lecture 3. But in any case, I advise the PhD students following the course to invest a bit in toric geometry, because it is very often a useful test ground for computing, for making computations or checking possible conjectures on problems that you are interested in. Okay, I end up with this first lecture of today by giving a few references. So first, the notion of energy in several complex variables showed up in a paper by Segrel that he was considering a similar setting in pseudo-convex domains of CN. And then the majority of what I said in this lecture comes from a paper with joint paper with Ahmed Zariai. In the next lecture, I will describe the heart of a paper with Berman, Buxom, and Zariai, which is this one. And finally, I will say a bit more words, but brief ones on lecture 8 on the contribution of Darvas, who studied the Mabuchi point of view on the space of Kähler potentials. Okay, so this is it for lecture, which one is it? Lecture 5, I guess. Maybe you have questions before we have a break, or not?
Actually, why is it the canonical approximant only weakly converging, whereas the other one is converging in a Borel sense? This is not.
It's the other way around.
No, okay. And where do you see the difference?
No, so what I said is that the canonical approximants converge in the Borel sense to the Monge-Ampère of the measure of the Monge-Ampère measure of the phi. But if you are working with in the Bedford-Taylor sense, okay, you forget about E1 classes. So if you are looking at a decreasing sequence of a perisomnic function, bounded perisomnic function, then it converges, but in a Radon sense, to the Monge-Ampère of the function phi. Okay.
Okay.
So there is no reason why this convergence would hold or should hold in the Borel sense. And maybe so an obvious example would require to slightly go outside of the bounded world. Take the case of the green function. Okay, the green function, the Monge-Ampère of the green function is well defined, and it has a Dirac mass at the origin, say in CL. Okay. Now I can it's an isolated singularity, so it's say almost bounded. Huh? Now I can approximate it by whatever you like, maybe convolution. So I have smooth freezing guys. The Monge-Ampère of those approximants, because they are smooth measures, they put zero mass to the point of the origin, while the limiting guy has a Dirac mass. So there is not convergence in the Borel sense. So once you have this kind of example in mind, you can cook up billions of counterexamples. Okay?
But what did you say about E1, the convergence to something to E1?
So the point, the strength, if you like, the extension from bounded to E1 works very nicely because the convergence of the canonical approximant, so very special approximant, is very strong towards the limiting measure. If you like, what you can do is that you want to prove something, say a certain Monge-Ampère of a sequence in E1, whether or not it converges towards the Monge-Ampère of the limit, a certain limiting guy. Well, you can cut out the approximants and the limiting guy by the canonical approximants and pass by the bounded world. And somehow you have two arrows where you have uniform control thanks to this Borel convergence. And it should work at the bounded level. And if it does, then by uniformity, you can get the convergence.
Okay. Thanks.